and welcome back. When last we left our hero, we saw that maybe there's an idea of not just locking in these 6 bits and saying that the binary point is 2 in from the right, but maybe there's another input on the side that can actually change where that binary point is. And that second input is the aha with floating point. So again, before we've locked in, fixed point, we fix it there. But what if I were able to also pass in another input, which tells you where the binary point might be? And that allows the binary point to, drum roll please, float. Float. It's not fixed, it can float. And that beautiful idea of it floating back and forth is the power of this representation. It's like another level of abstraction. Rather than locking it here, I'm now abstracting away and saying, what if it's more general now? I can now move it where it is. So that's just really amazing. So let's look at an example. Here's 0.1640625. It's in binary. If I represent this in 5 bits and I choose where to put the binary point, okay? So here is this. I've got 0.0, you see this here? 0.00101001, 10101, and then all the zeros. So all I kind of need to know, see the guys in blue? All I need to know is I need to somehow send these 5 bits. If I could somehow send those 5 bits, I don't need to send the zeros before it or zeros after it or over here. I don't need to send those. It's just, but default is always 0. I almost need to send you where the energy is, where are the 1s and zeros that are interesting. But I kind of need to freeze it on the left side and the right side with 1s, and there's zeros outside of it. So if I could just send that set, and with my other input, that's the key idea. I tell you, oh, the binary point should be 2 to the left of the leftmost 1. So I would say like, somehow -2. Sending it -2, that tells you it's over there. And on this guy, I'm sending 10101. So that's kind of cool. So you can imagine sending 2 inputs. This is the energy, I say what the energy is, and this is where the floating point would be. And that's amazing. That's amazing. So that is the idea. We're gonna have some fields to our representation. One field tells you kind of where the energy is, and one field tells you, in a way, the exponent, tells you where it is. It's multiplied times 2 to the what, right? It's times 2 to the -2. Here's 2 to the -2 because it's 2 over, okay? It's the quarter. This is times a quarter. So what it's saying is, it's saying, I want to be able to have this exponent for where that moves. Every time I move it to the left, it's multiplying by a factor of 2. So it's really what 2 to the what? 2 to the 0 says it's exactly where you think it is. 2 to the 1 says move it 1 to the left. And now I have a 0 to the right, etc. Isn't that cool? Well, 1 to the right. Move it 1 to the right, I guess is what it is. Move 1 to the right, okay? So because the binary point, where it is different from the actual stored bits, what I call the energy, now I can do large and small numbers. Now I've got the first thing. I can do really small numbers and really big numbers, or big and small, and I got it. So let's now review scientific notation in decimal. Back in the old days. Now we're in, I think we're probably in physics class, maybe AP, maybe chemistry back in high school, 9th or 10th grade. If you remember, here's some words, just to remind you what these words mean. I had a decimal point, that's the obvious thing. I've got the radix, which we call the base. I've got the exponent, and I've got the mantissa on the left, okay? So, if I live in normal form says that I always have a single digit to the left of the decimal point. So I don't have, if I wanted to store 1 times 10 to the -9th, okay, so, or a nano something, I wouldn't store it as 0.1 times 10 to the 8th, and I would not store it as 10 times 10 to the -10th. Even though they're equivalent mathematically, I would not do that, because they're not in normalized form. So we're gonna go with a normalized form there. So that's pretty cool. So let's see what that looks like when we go to binary. Same idea. 3 out of those 4 words are exactly the same. Mantissa is there, the exponent's up there, the base is base 2, not base 10, and now it's the binary point. We call this floating point numbers, officially. Floating point numbers, and if you've ever seen the phrase in C, float, that's it. This is what happens. We're storing this story in this way. We're storing in this way in normalized form, where on the left is always going to be a 1. That's the important thing. Always going to be a 1 to the left of the binary point in normalized form. This is it. I feel like it's such a delight to teach somebody something new for the first time, and this is it. This is the beginning of what we call the IEEE floating point designation. So here's normalized form. You're gonna say, but Dan, if every number starts with 1 point something, you might say to me, why do you have to transmit it? Why would you store the 1 on the left if it's 1 on the left always? There's always gonna be a 1 on the left unless it's all zeros. There's gonna be a leading 1. Why store it where it's always gonna be 1? And you're like, you're right. So we actually don't store it. We only store the number to the right, which is the significand. So the 1 point is always kind of default there. Y is our exponent. So this exponent goes here. Here's our significand there. And you're gonna say, well, Dan, we probably should have some negative numbers too. And to make this easy, what we're gonna do is, let's actually use a sign magnitude model. So that left is a sign bit. So there we go. S is your sign bit. Bloop. Exponent are these 8 bits there that returns 2 to the y, and the significand are the x's represented there with 23 bits. That's a lot. 1 point, 23 more bits. That's quite a bit, actually. It's pretty cool. And by the way, what's this last bit controlling? What's that last bit? If it's always 1 point something, that last bit is 2 to the minus 23. So it's 1 plus 2 to the minus, if I only have a 1 here and have zeros all in here, that last guy is 2 to the minus 23. If you think about that, 23 bits there on the right, it's that. It's 1 point this, 2 to the minus 23. Remember there was 4 bits to the right, and it was 1/16, it was 2 to the minus 4. Well, 23 bits across, 2 to the minus 23 is the guy all the way on the right. What can we do? Well, just this. Nothing special, nothing more than that, no special cases, which we're gonna see in later lectures. We can get to 1.2 times 10 to the minus 38. Really small numbers. And up to 3.4 times 10 to the 38. That's amazing. This is really cool. Now, you're gonna say, well, Dan, what if they're too large? That's pretty good. That's pretty good. And we're gonna see the ain't no free lunch coming up back again. But we'll talk about that in a second. So what if they're bigger than that? What if they're either bigger than the high side or smaller than the low side? Well, that's overflow. I want to store a number bigger than that. What if I double it and double that? And I can't always and forever do that. Double that. I got a fixed bit width. At some point, it's going to be bigger than I can store. We call that overflow. What if it's even smaller than it? What if it's half of that on the negative side? Half of that. Actually, no, it should be double a negative number. I'm sorry. If you double the negative number and keep pushing the left side, it's also overflow. Some people call it negative overflow, but it's also overflow. On the big sides, on the ends towards infinity, always overflow. Sometimes the left, they call it negative overflow. What if they're too small? Aha! Underflow. You thought that the negative infinity was underflow. It's not. If that's overflow, that's not underflow. Underflow is towards 0. What if I take a number and have it, and have it, and have it, and it keeps getting smaller and smaller? At some point, I reach the limit of what I can do, and one past that is underflow. I would say it's 0, even though there is some number. Nope, the closest number that I can store to what you're asking me for is 0. So I kind of underflowed to 0, and that's a problem, because it means that, I made some fractional amount, but then it says 0, but it's not really 0, it's close to 0, and that's an issue. So again, underflow is close to 0, overflow is on the sides. We'll just call it overflow in 61C rather than negative overflow, but that's right. What would help? Think about, what would help reduce the chances of overflow and underflow? Throw more bits at it, right? Throw more bits at the problem. So here is the IEEE 754 floating point standard used in every computer you have access to. That's it. Sign bit, 8 exponent bits, 23 significand bits. That's great. By the way, just a refresher, 1 is going to mean a negative number and 0 is going to be a positive number. So that's pretty cool. Now, we mentioned this before, to pack more bits, the leading 1 is going to be implicit. Remember, that's normalized form, and why store that 1 if it's always going to be a 1? So that's pretty cool. If I actually want more, if I want to have more resolution, I want to reduce the chance of overflow or underflow, throw more bits at the problem. Call it a double. So we'll have actually a double for our significand for that. And I have 52 bits for that. So what's always true is the significand is between 0 and 1 for normalized numbers. Because if you remember, it's 1 point, all those bits, 23 or 52. Think about that, 1 point this. So the significand is point something. Goes from 0 if it's all zeros to all ones, but it's still a fractional number. It's probably, with 23, it is 1 over 2 to the 23 away from 1. So it is, I don't know how to say that. It's a number very close to 1. How close is it to 1? 1 over 2 to the 23 away from 1. That's how it is. And here's an interesting thing. 0 has no leading 1. We said this weird case that 0 has no leading 1. So we're going to reserve the exponent value of all zeros just for 0, which is great. So now I have exponent of 0. So I want to restore 0. There's a 0. There's a 0. And wait, sign bit. Do you remember our issue with sign bits? With sign magnitude? I got 2 zeros. What do you think? We got 2 zeros here too. So here's the other part that's interesting. If 0 is the smallest exponent in terms of the bit pattern, and we go up, wouldn't it be nice if all zeros, here's the thing, all zeros were the smallest one, and we kept going up continually, not having to wrap, like remember signed? It starts in the middle, goes up, and then it snaps over here and does this thing. I want it to be 0, all zeros is the smallest one, and go up. But if I want the small, here's the part that's a little weird, I want that smallest one to be in the negative, because I want to do fractional numbers, right? I want that to be 2 to the negative number. So if I want all 0-bit pattern to somehow be a negative, how's this going to work? Okay. So here's the designer. The designers went back to the drawing board and they said, we want to use, if I have no floating point hardware, by the way, back in the day, they used to have explicit floating point hardware, and we still have that. But if I didn't, in the early days of machines, they didn't have special purpose floating point hardware. They just had a normal CPU. But they want to be able to use the CPU to compare and do things, do some manipulations with floating point numbers. So they came up with the idea that bigger integer exponents are bigger numbers, smaller ones are fractional numbers. And they thought to themselves, they said, oh, thinking about the odometer, the only way to do that is that bias notation. So therefore, kind of a really small bit patterns, very few numbers, low bit patterns, like you're driving the binary odometer a little bit, that should be a negative number. And a high thing should be a really big positive number. Well, that's a bias model. If you think about that, that takes this, here's 0 in this, and here's all 1s. And if you shift them down by some offset, then this is going to be overall a negative number, and this will be a positive number. If this is from 0 to 55, then roughly this would be kind of 128 to minus 128-ish, somewhere on there. And that's pretty good. So we'll shift it down by some bias and we'll get what we want. Love this. So bias notation, and the bias is subtracted. And we've got 8 bits. You remember how we did 8 bits before? 8 bits is 2 to the n minus 1 minus 1. So 2 to the n minus 1. So 8 bits, 2 to the n minus 1, n is 8. That's 128, minus 1 is 127, so we call the bias 127. What that really means is you subtract 127 from the value of that. So you look at the unsigned value, subtract 127, and you've got your actual number. So that's it. So there's our equation. Let's take a look at our equation now. This is actually a kind of interesting thing. Minus 1 to the s. When s is 0, minus 1 to the 0 is 1. So that's just a normal positive number. If s is 1, it's minus 1 to the 1, which is minus number. So actually, that's a kind of a cool way to think about the sign bit. It's minus 1 to the sign bit. Times 1 plus significand. You remember this? There's the implicit 1. Times 2 to the exponent, whatever the raw value is, minus your 127 bias. That's it. Folks, that is the IEEE 754 floating point standard. There's still some more details there, but that's pretty cool. And double is exactly the same. It's just you have more bits for the significand and more bits for the exponent, but exactly the same equation. That's pretty cool. And quad is bigger than that. Same idea, just more, again, bits for the exponent, more bits for the significand. Let me introduce you to my colleague, Professor Velvel Kahan. He's the father of the floating point standard. UC Berkeley, IEEE standard 754 for binary floating point arithmetic earned him the Turing Award, the Nobel Prize in Computer Science, for being the leader of this, floating point space. The ecosystem was chaotic before his team of folks said, let's kind of normalize this so that if I calculate something on one computer and bring it to the other computer, I've got the different number. This was happening all around and so I would try to compare, I did a trajectory and it landed here, and yours landed. Why? Because the way the algorithms were the same, but the way the floating point was done below the line in the hardware was different on every machine. He said, that's crazy. Let's have a standard. Let's have a way that my calculation can move to your computer. Remember porting was an issue? Well, it's big Indy and small Indy and all these weird things that are different about this. Ints are different sizes. It's even worse back in the day in the floating point space. Your machine was completely different from our machine. We couldn't trust our numbers. So the scientific community said, we gotta centralize this. He led the team to centralize it, came up with IEEE standard 754, and won the Turing Award back in 1989 for him. Amazing, right? Amazing work. So we're gonna see now more details about this. We're gonna see, does that cover everything? Well, that's almost 90% of it. In terms of intellectually, 90% of this. But there's a lot of interesting ideas. Now that you know the basics of floating point, where can we go with that? We're gonna see that in the next set of videos. See you there.